So today what we want to do is pick up on the topic of aliasing again that we worked through last time. And at the end of Monday we were heard aliasing, we saw where it comes from, the sampling process, and we took a simple example of a single frequency sinusoidal signal and used that to study how we can predict where in the frequency spectrum, if the signal aliases, where does it go? And so today what I'm going to do is do a slightly more complicated example like that. Includes phase and sines instead of cosines. Walk through that graphically with a bit of Fourier transform knowledge and see if we can see graphically what's happening, what the explanation is, and then look at it mathematically, analytically, and see if we can come up to the same answer. And then once we've kind of got a good grasp on aliasing, how it works, and how to predict its effects, then we'll start talking about, well, in the real world, how do we keep this from happening? Because we know it's a bad thing, it's a distortion, it's a problem that we can't undo. And so we'll look at some of the methods that are used in practical sampling to see how we can keep that from happening. So that's what we'll be up to. Questions on stuff we did before we move ahead? No? All right? Okay. So if you understood the example last time, this is going to be similar, but there'll be a few extra details that make it slightly more complicated. So this is another aliasing example for a single frequency signal. And let's start off with a continuous time signal, xc of t, that is a, well, let's give it a magnitude of 4. We'll make it a sine instead of a cosine. We'll make it a 200 pi t to pi. And we'll give it a little phase this time, minus pi over 3 for phase angle. And we want to know if I sample that signal. F sample was, let's use 150 hertz, which is a ridiculously low sampling rate, which is simplicity for example. Does it alias? Yes. And where does it alias to? Ah, there's the rub. What does the signal look like after it aliases? And how does that aliasing, well, we see it affects the frequency. How does it affect the phase? Does it affect the phase? Those are the kind of questions we want to explore a little bit. And so, first off, I want to make one simplification, because I know I'm going to go over here and start drawing spectra. When I draw spectra, cosines are a much easier thing to draw spectra of than sines, because the Euler identity for a cosine is simpler than the sine one. So let's just make the trigonometric substitution, the equivalent cosine version of this. Cosine, let's say that's, and let's break out the frequency. What is the actual hertz frequency of the signal? 100 hertz, right? 100 t minus pi over 3. Now when I convert it, change from a sine orientation to a cosine orientation, what do we do with the cosine? Subtract how much? Pi over 2, yeah. The cosine's 90 degrees ahead of the sine. So I'm going to have to take off a pi over 2 to make that substitution. So this is really a 4 cosine 2 pi 100.
Minus 5 pi over 6.
T, and yeah, minus 5 pi over 6. So 5 pi over 6 is our phase for a cosine, or minus 5 pi over 6. Okay. And so we've got our friend Mr. Euler, who tells us if I want to express this cosine as a bunch of complex exponentials, cosine theta. What's that in e to the j things? Blue renders. E to the j theta.
Plus e to the minus j theta.
E to the minus j theta with a plus sign. And all over 2. Right? So this is 4 then times, we'll bring the 1/2 out front, and I can express that cosine as e to the plus j 2 pi 100t minus 5 pi over 6. Let's make that a little clearer to see. 5 pi over 6. That's the positive e to the j, and the e to the minus j, same thing. Minus j, 2 pi 100 t minus 5 pi over 6. So we just use the Euler identity, and let's simplify that. That looks like e to the plus j 2 pi 100 t minus 5 pi over 6. That's our e to the plus j 1. I've got some minus things going on here. So I'm going to do something kind of weird here. I'll make this a positive exponential. E to the plus j 2 pi times minus 100 times t. And minus is a positive, so I have a plus 5 pi over 6. And hopefully you'll agree with me those are equivalent.
You can't pull 5 pi out of 6 out of the whole equation.
Was it? Say again?
The subtraction and addition of the 5 pi over 6 constant, I don't think there's an easy way to pull that out.
Can't pull that out of both, but I am going to pull it out of each eventually. Well, let's do that. Let's do that. So what I think we're saying is I can make sure I got to my e to the minus j 5 pi over 6. I can bring that out in front of that because when I multiply exponentials, I add their exponents. E to the plus j 2 pi 100t. So hopefully we'll agree that those two are the same. And on this one, I can pull out an e to the plus j 5 pi over 6, multiplied now by the original e to the plus j 2 pi minus 100 t. And this is actually a convenient form for me to do the Fourier transform on this so we can see what its spectrum looks like. So this is the spectrum of our continuous time signal. Now, we haven't sampled it yet. We don't know that it's going to alias, but we'll start seeing that. All we've done is some trigonometric and mathematical manipulations. So nothing physical has happened yet. Just lots of different ways to write the same signal. Everybody okay with all those steps? Okay, bad news for you. We got to remember some Fourier transform theory. Let's try this out. Fourier transforms. Various properties. I want to know what's the spectrum of this signal. And how do I draw the spectrum of the signal? Now, last time we said, oh, it's cosine, it's a couple impulses, and we're done. Well, this time we can't, not quite so simple, which is why we're going through all these steps. So rather than doing some hand-waving arguments, let's do it by some good old-fashioned theory. So I want to find a Fourier transform of this mess. Okay. It looks scary, but it's not. Let's start with simple. What's the Fourier transform of 1? One at a time to me. What's the Fourier transform? Delta of f, an impulse in the frequency domain at frequency 0. And if I scale it 2 as a Fourier transform of it, it just scales, gives a weight to that delta function, right? All right, so got the two handle. What about this e to the j thing going on in there? 2e to the j, what is that? 2 pi, let me just use the general frequency f0t. If I multiply something in the time domain by e to the j 2 pi ft, there was a property for that in Fourier transforms. Remember what it was? Frequency shift property. When I multiply by e to the j 2 pi ft, I take my Fourier spectrum, and everywhere there was a frequency, I shift it by this frequency. So I got this taken care of, I got this taken care of. I've got addition, well that's just adding in the other domain, so if I can take care of this, I'm good to go. Well, before I bite off that e to the j thing, which scares me too much, if I just argue, what if I multiplied this thing that I've already got, it's e to the j 2 pi f0t with a 2 out in front, what if I multiplied that by a constant c? What happens to this? Now, this is a constant, it's not a function of time. Just scales it, right? 2c delta of f minus f0. It just scales the Fourier transform. Well, I'll argue that 2e to the j, what is that? Minus 5 pi over 6. That's just a numeric constant. It's a complex value, but it's a singular value. It's a number. It's a complex. It's a scale factor. And so it works the same way. E to the j 2 pi f0t. It just scales that. So 2 e to the minus j 5 pi over 6 times a delta of f minus f0. So this is the Fourier transform of this term, and a similar Fourier transform will give me this term with a different scale factor and a different frequency. So we've got everything we need to draw a picture. And what is that picture? Well, Fourier transform of this is a impulse at shifted to this frequency f0, the frequency that I had in here, 100, with a 2e to the minus j 5 pi over 6 complex scale factor, which, if you want to use a shorthand notation, is 2 angled at minus 5 pi over 6. Right? So that just means that my impulse has a complex weight. It's okay. And this one similarly gives me an impulse, now at frequency minus 100, with this scale factor, e to the plus j 5 pi over 6. Boom. So that was 15 minutes to come up with the Fourier transform of a sine with a phase angle. That was a lot of work. Everybody okay with what we did? Now that's the brute force step-by-step way. If I could have just said, there it is, there's a spectrum, you would have taken my word for it, right? I wouldn't, but okay. All right, now we're ready to sample it. Let's sample that signal. What happens when I sample that signal? I go into the digital domain. And we know how to relate digital frequency to analog frequency. What was my sampling rate, 150 hertz, is now digital frequency 1. What was half the sampling rate, 75, is now 0.5 in digital frequency, and so on and so on and so on. So now those are connected once I tell you the sampling rate. And we sample the signal, and sampling does two things. Tell me the two things sampling does to my signal, to its spectrum. What happens to the spectrum? What does it do? thing really important, one thing small. What happens to the spectrum when we sample? What did you do on your homework problem last night? Makes copies, right? Where do the copies show up? Oh, this is very important. We make copies of the spectrum. Those spectrums are centered at every integer multiple of what? Sampling rate, which in digital frequency is what number? Every multiple of 1. So I'm going to pick this up, I'm going to move it down here into the digital realm, and I'm going to make copies of it centered on the sampling rate, or centered on 1, 2, 3, all those integers in the frequency. Very important. That all of sampling theory, that's, other than Nyquist frequency, that's factoid number 2 that we really want you to come away from this sampling discussion, knowing that when we sample a signal, its frequency spectrum becomes repeated copies of the original. Now, according to our little model of impulse sampling, we also end up scaling it by the sampling frequency, or 1 over t sub s. So what we get is a scaled version of that original one. It was scaled by 1 over t sub s, or in this case, multiplied by fs. Hasn't changed the angle, just changes the magnitude. And now we make copies of it, copies of that complete spectrum, where every copy is centered on an integer multiple of the sampling rate. So we pick up those, make a copy, center them on capital F equals 1, and capital F equals 2, and capital F equals 3. And make copies and go in the negative way too, centered on -1, and -2, and -3. And I'm going to turn off the lights and help you read some of the fuzzy things up there, because it's kind of important, the fine print. And for some reason the projector's a little blurry. So, important. This was 2 angle minus 5 pi over 6. That's the same thing as down here. Now 300 angle minus 5 pi over 6. And when I made a copy of it, this copy up here is 300 at angle minus 5 pi over 6. And the copy down here is angle minus 5 pi over 6. This one that has a plus 5 pi over 6 there got copied and showed up here. So this is a plus sign. And there plus 5 pi over 6, as is the one down here, copy it showed up down here. And so get those right. Yeah.
So the placement on the x-axis is the frequency of sampling.
So this is frequency, and what was frequency 0 now becomes the center at every integer multiple of the sampling rate.
Okay.
And so I should also show copies centered around 2 and 3 and 4 and -2 and -3 and -4, but it's going to get too many arrows to confuse things. Okay. So that was the key to the first homework problem that there was last night. We made copies of the spectrum and center those copies at the sampling rate. Yeah.
I can't really see from here. What are the signs on those impulses in the digital frequency? On the phase? Is it all positive 5 pi over 6?
So no, that's where we were going. So this one's negative, this one's positive, and that one's positive. This one's negative, negative. I'm sorry, this one's positive. Sorry, this one's negative, and that one's negative. The important one is this is positive, this one's negative. Because I'm going to throw the rest of these away. Remember, when coming out of our sampling system, out of our digital signal processing system, we're going to run, we don't want all these spectral copies. You know, part of our reconstruction process, we're going to go through a low-pass filter. Who's going to throw away everything that's outside the Nyquist rate, or outside what we call the principal range, which in digital frequency is +1/2 to -1/2, or analog frequency plus 75 minus 75. And what we'll also do is scale the magnitude response of that, technically, to take back out the 1 over t sub s scaling that happened here that made us go from 2 to 300. We'll make this 1 over 300 and take it back out. So when I multiply this spectrum by this spectrum and we filter it, only these two center impulses come out. Their amplitudes get scaled back down where they were. But notice they're at a different frequency and the phase isn't the same. Phase sign flipped. That's the punchline. So that change in frequency, that's the aliasing. The aliasing came from making these spectral copies. And by keeping track of the phase as part of the process, we see which one, the positive phase or the negative phase, ended up over here on the positive side. Let's bring those lights back up so we can see the board. Everybody okay with how those copies worked and why those phases ended up that way and why we've only got two impulses left there? All right. And then working our way backwards.
Professor.
Yeah.
How did you determine the cutoff frequencies for the bandpass filter?
For this guy?
Yeah.
Okay, this is going to be a low-pass filter. Its job is to throw away copies of this frequency spectrum that are outside the Nyquist rate. And so I'm setting its cutoff right at the Nyquist. And this was what we called the principal range, because actually we know everything, and if I know this, everything else is a copy of it. Yeah.
Is it practical to set it right at the Nyquist, or would you want to
Is it practical to sample right at the Nyquist rate? Monsieur Nyquist would say, you can do that.
And then the low pass filter, is it practical to do it that way?
Oh, is it practical to set the cutoff rate at the Nyquist rate?
Yeah.
You can set the cutoff frequency there, you just can't build that filter.
Yeah.
You can't make a perfect, sharp cutoff filter. Well, actually, not only can you not afford it, but you just can't build it. It's a idealization. And so that's one of the issues. When we get the example finished, we'll talk about, okay, how do we deal with the practical world where I can't make that filter? And so because of that, you can't just sample exactly at the Nyquist rate, and you've got to deal with the fact that you've got imperfect filters, and there's some games we play for that. Okay, but everybody's all right with this? Yeah.
So that cutoff frequency comes from the sampling rate?
Once we define the sampling rate, then that defines what cutoff frequency we need to do the recovery process.
I see.
Yep, they're joined. Okay. So we went from those top impulses to the bottom impulses. We didn't change the magnitude, but things moved in frequency and things shifted in phase. That's kind of weird. Well, so what is this signal? Let's go backwards. If I gave you this spectrum, we'd say what's that signal? Well, two impulses at the same frequency with this phase. We would call that a cosine. Right? It's a cosine. We call that x alias of t. Looks like, well, two impulses with weights of 2 give me a 4. Cosine 2 pi. Well, now the alias frequency looks like we're at 50 hertz t. And our phase, well, if you didn't know this, you've got a spectrum, impulse spectrum of a cosine. Where do you get the phase from? You get it from the positive frequency side. So the phase is plus 5 pi over 6. So that's what the continuous time version, if I just sampled that signal and then spit it back out, this is what would come out. A different frequency, same amplitude with this phase. All right. After the filtering. All right. Now, if you wanted to put that back in your lovely notation with the signs, all right, well, that's 4 sine, let's call that 100 pi t, theta plus 5 pi over 6. And now we have to add back that pi over 2. All right. Which gives me a total angle of 8 pi over 6 or 4 pi over 3. So where is that? 4 pi over 3. 4 pi's over 3. It's over here somewhere. No, that's kind of, I don't like big angles like that. So let's scale that back. Let's use an angle over here in the first quadrant. So the sine of this angle is the opposite of the sine in that angle. Take off 180 degrees. I'm thinking I'll call that minus 4 sine 100 pi t minus pi over plus pi over 3. All I'm doing is saying I don't like to express a big angle greater than pi, but greater than pi. So I want to use a smaller angle. If I take off 180 degrees from a sine, I have to change its SIG in out in front. And I get the same answer. That height is the same as that height, just a different sign. We're just using trigonometric identities here. Okay. So that's what we alias to. And if we were to convert that to discrete time signals in the digital realm, or x sub n for that, which is aliased. Is what? Minus 4 sine 2 pi 50 over 150 n plus pi over 3. Is our digital alias frequency is the analog one divided by the sampling rate. Right? So, or if you prefer, minus 4 sine, and we'll call that 2 pi n over 3 plus pi over 3. So the discrete time signal that we would get inside before we send it out would have been this one. And double check. Yep. All right. Oh, that was hard. Okay, that took us, whoa, whole half an hour, yeah.
So I'm still lost at what point did you know you were alias? Or you still having?
Well, that's a good point. I guess I don't, I get really suspicious because the signal that came out is a different frequency than what I put in. So that tips me off. Now, what we'll do is take the shortcut and answer exactly your question. You don't want it to take you half an hour to do one of these problems, right? So let's just do it analytically, mathematically. Here's how we could approach it. There's our continuous time signal. So 4 sine, back to where we started from, 200 pi t minus, where do we start with? Minus pi over 3. Right. And our sampling rate was 150 hertz, bytes. So we ask ourselves, what's our analog frequency? And you tell me it is, again, 100 hertz. And so we ask ourselves, does it alias? So we ask, is is the sampling rate greater than 2 times the highest frequency? Is the sampling rate greater than twice that? No. Therefore, it is going to alias. So that's how we check. And right off the bat, we say, okay, and as soon as I know what alias is, I know the frequency is going to change. It's moving. All right? So then we can answer, where is it alias to? I'll get out of the way here. And so we can predict that. We have an equation for that. What was that last time? Anybody remember? Flew up there on the board real quickly at the end of the day on Monday. Probably we were dashing out, trying to write it down. We take our original frequency and we subtract off an integer multiple of the sampling rate, where this guy k has to be an integer, and it's got to be big enough so that this alias frequency is in the principal range. Another way of saying that, inside the Nyquist rate. Or magnitude of F alias has got to be less than Fs over 2. Could be negative. All right. So what do we do? Button that up. So for us, we're going to find an F alias. That was our original frequency, 100 minus, well, I think just 1 times 150 will do it. Which gives me a minus 50. And I'll stop using this marker that doesn't work. Let's do this. So we know what frequency it's going to go to. Let's try it over here. So our alias signal, X codex alias of T. Going to be a 4 sine 2 pi times our new alias frequency minus 50 T. And our phase minus pi over 3. Well, what we're saying is this guy aliased over to here. Right? That's what we're seeing there. And so technically, if I asked you what's the continuous time version of the alias frequency and you gave me this on the exam, you would be 80, you'd be 90.25% right. But I don't like this. There's a negative frequency. I don't like negative frequencies. So we want to make this a positive frequency. Well, I'm going to have to invert this entire angle argument to do that. Right? So I'm going to need a 4. I'm going to need a sine. I want to invert that whole thing to get a 2 pi plus 50 t. But if I invert the whole thing, this becomes plus pi over 3. And now I've got to ask the question. I just arbitrarily took something that had a negative angle and said, no, it's got a positive angle. Did that change the magnitude of the sine of that angle? No, but it did change the sine, SIGN, of the sine of that angle. So I have to account for the fact that I inverted the angle argument by putting a negative out in front. And hopefully that matches this. And then once we have this, we could go through the same argument to get to the discrete time version. Right? Or do it even faster. Work in the whole thing in the digital realm and say that our digital frequency of that signal coming in is the original analog frequency, well, not E, let's use F0, over the sampling rate, which is 100 over 150, which is 2/3. And we can ask ourselves, does that signal alias? And it does. For digital frequency, again, we want to see is F0 got to be less than what? Half, Nyquist rate. Which it's not, so it aliases. And where does it alias to? Well, F in continuous, or excuse me, discrete time frequency, it's the starting frequency minus, well, where's our equation? It's this equation, but the discrete time version, where all my frequencies are normalized by Fs. Normalized by Fs. That's capital F0. Normalized by Fs. Oh. That's just an integer. Same thing until we get in the principal range, the magnitude of F alias is inside the principal range. Fs over 2, 1/2. And so for us, F0 is 2/3 minus, well, 1 will do it, minus 1/3 is our F alias. And so our alias, I'll get it over there so you can see that, is again, well, what was it? It was 4 sine 2 pi. Now that F alias, which is minus 1/3, n discrete minus pi over 3. Right? Keeping the same phase, and then by the same thing we just did over there, I don't like negative frequency. It's the same as minus 4 sine 2 pi n over 3 plus pi over 3. That was a lot of work. These are a lot of time. But if you understand this example, then the 3 homework problems that you have next are very doable. It's pretty much the same thing. Make sure you know how to do it. But again, the big concepts. When we sample anything, we make copies of its spectrum, repeated every integer multiple of the sampling rate. If we violate the Nyquist criterion with that, then something's going to alias, and we can predict where it's going to alias using these 2 formulas, whether using analog frequency or digital frequency. Question?
If your sampling frequency is very slow, could you get multiple alias frequencies?
If you're sampling, there will only be one alias frequency. If you're sampled really slow, you're saying, can you get multiple spectral copies in the principal range? No. Because while your sampling rate's going down, so is your Nyquist rate. It's squeezing in too.
I see.
is, under, when you're doing the F0 minus K, where did you choose K to be 1?
I choose K to be big enough until this guy gets a magnitude that's within
Okay.
Nyquist rate.
Thanks.
Yep. Okay, other questions? Yeah.
So no matter what, using that method, you can find the alias frequency as long as you start from a high enough number and like go down until you find.
Keep going until you get into the principal range. Sometimes it'll take more than one, depending on the relationship between the sampling rate and your highest frequency. Okay. With the 10 minutes-ish left, we'll talk about how you deal with that in the real world. Because there's a problem, and that problem is that all this stuff is lovely, but if you're designing a digital signal processing system and you're taking in a signal from a sensor, you may not have control over the signal that's coming in. And there's also this time band limit theorem that says there's no such thing as a signal that's band limited in frequency and time limited finite length in time. Therefore, if I have a signal that turns on and turns off, by definition, it has an infinite spectrum, and it's going to alias. And so, what am I going to do? So what we need to make sure of is, well, we don't have to be perfect, but we want to make sure that the amplitude spectrum of our signal is at least negligibly small by the time you get to the Nyquist rate. And what's negligibly small in a digital system? Well, if I'm going to digitize it, and this much voltage range represents 1 bit of my A to D converter, what's going on in there can do whatever it wants, as long as it doesn't exceed, well, actually half a bit, depending on the rounding technique, but 1 A to D count. So a little bit of dither is okay, but that doesn't take much if you have a high resolution system. And you generally don't have exact control over the incoming signal. You know, that may be coming from a sensor that you don't know what it's going to look like, you can't control it, or even if you could, you don't know if there's going to be any noise coupled into the line, and noise inherently has a high frequency component, and that will alias. So what do? Well, most critical digital signal processing systems will have an anti-aliasing filter, literally. A low-pass filter stuck in front of the A to D converter whose job is to make sure that no signal that could alias is going to get in before you sample it. So any signal with frequencies above the Nyquist rate, we're going to chop out with an analog filter. Our other choice, which we can use in conjunction or by itself, is choose a high enough sampling rate, raise the Nyquist rate until it gets big enough that everything that's in that mushy signal is okay, it's not going to alias. You can oversample. Well, let's look at how the idea here. Yeah.
So like with an anti-aliasing filter, that means like you just wouldn't get high frequencies at all.
You would throw them away before they got in.
Okay.
And here's the picture. So if you have a signal that has some higher frequencies, at least something that's above the Nyquist rate, we know that if you just try to sample that, we're going to make these spectral copies. And where those spectral copies overlap, this stuff is aliasing and distorting our signal. So we would find that unacceptable. So what we do is literally put an analog filter in front of it that has a low-pass filter that cuts off the stuff that might alias. Anything above the Nyquist rate gets thrown away. Now that signal that filtered signal can replicate safely. We make the spectral copies, we don't get any overlap, we don't get any aliasing. Now, a couple assumptions. We assumed that this stuff up here was something we don't care about. If we really did care about that, we should be sampling at a higher rate so that the Nyquist rate is higher. But if that's truly noise or stuff we don't care about, we're going to throw it away to keep it from aliasing and messing up our signal, the good parts. Now, this is the kind of anti-aliasing filter that we'd like to make, which is getting to your point. I would like an ideal low-pass filter that has a magnitude response that's 1 and flat everywhere in the frequencies I want to let through. That's exactly 0 at higher frequencies, anything above the Nyquist rate. That would be 87 billion dB attenuation. and goes instantaneously from 1 to 0 right at the Nyquist rate. We call a brick wall filter. Very sharp cutoff. You cannot make that filter. It's physically impossible. Not only is it too expensive, but you just cannot build that filter. It can't be made. You can try to approximate it by throwing a lot of money at it, but any analog filter is going to have some degree of, well, there might be some ripple in either or both pass band and stop band, depending on what kind of filter you choose. Any ripple in the stop band means I'm letting signal through here, and I'm letting signal through there. I'm not attenuating perfectly. I'm letting stuff through that's going to alias. And because I can't make a super sharp cutoff, I'm letting this stuff through that's going to alias. And not only that, I'm throwing away stuff I was supposed to keep. So, not good. All right. So those are the practical limitations of real live analog filters. Ripple in pass band, stop band, finite transition width. I can make this transition width sharper by throwing more money at it. Like here's an example of a Butterworth filter. Butterworth filters is a style of analog filter that's nice because it doesn't have any ripple, but it's slow at rolling off, and how quickly it rolls off depends on the filter order. The higher the order, the faster the roll off. Well, adding an order means I'm adding another op amp and resistors and capacitors. I'm physically adding more hardware. So if I want a high order analog filter, I'm throwing money at it. Okay. So what do we do in the real world? Well, we put a lower order practical anti-aliasing filter in front of the AD converter, and then use a higher sampling rate to make that good enough. And there's shades of gray on this. As we talked about in the CD example, you can raise the sampling rate a little bit to give you some elbow room, or there's actually techniques where you deliberately oversample by a lot to make it even easier. And let's see if in 2 minutes we can explain how that works. So here's our sampling thing, picture as we change the sampling rate. I sample a signal, it has this spectrum, I'm making the spectral copies, right? And throw in the equivalent digital frequency. Now if I sample at a lower sampling rate, here's a picture where I'm keeping the analog axis the same. So this frequency here is the same as this frequency here. If I change the sampling rate, the width of the signal spectrum doesn't change, the copies get closer together, right? If I use a higher rate, they spread out. So first thing I can do, as was done in the CD rate, is don't design with just a Nyquist rate sampling, but use a slightly higher sampling rate so I can put a gentler roll-off, low-pass filter in and still be okay. That's the least I should do. All right. If you look at this from the other side, from the digital framework, if I increase the sampling rate of a signal and keep that digital axis the same, so 1 is always 1, when I up the sampling rate, things again get spread further apart, but notice the width of my spectrum is kind of squeezing in because I've constrained everything between, I've changed the sampling rate, but squeezing it in there. Well, if you have a signal with a finite bandwidth and maybe some noise above that bandwidth, then you put it through a gentle low-pass filter for anti-aliasing, well, what's going to happen? Come on. You'll filter out some of the noise, but if you don't choose a high enough sampling rate, the copies are still going to overlap, the noise is going to overlap, and that will alias into your system and mess you up. So, well, I could choose a really high sampling rate, at least that puts the spectral copy way up here, or we do this. We use the same low-cost filter and alias, and you use a sampling rate that's chosen not quite to be as high as I thought I was going to need there. I'm going to let it alias, and then I'm going to use a digital filter to throw out the alias stuff, because I can make a digital filter a high-order digital filter very easily. And so we'll do that. We'll let it alias, put a digital filter in, throw away the alias stuff, and then if my system can't sustain this high sampling rate, I'll throw away every other sample, and it'll be half the sampling rate. Or throw away, keep one out of every 4. My sampling rate drops by a factor of 4, which spreads my spectrum back out. And I have the old spectrum I wanted, without the alias stuff, running at a low sampling rate. And that's how CD players work now, or CD recorders work now, using this combination of oversampling and digital filtering and downsampling again. We'll talk about this some more. We'll talk about practical A to D converters, and then how we do the other side, reconstruction, on Friday. See you then.